Well, welcome everyone again to the last of our 3 rPlum workshops, and I'm joining you from Ngunnawal country here in Canberra, and like to welcome you all wherever you are around the world. And I won't carry on too much, but I think Marco is going to take us through the rest of what he's got in mind. I'm aware a lot of people got a bit lost in the last workshop, but don't worry, because there's, I think the real positive about that is that Marco, who's our wonderful modeler and is writing all this software, gets a better understanding of what the end users are actually encountering. So that's really helpful for him to understand the difficulties that we have. But also it helps us to understand also that there's a lot that goes in to something like rPlum. And it's not a simple thing, and it's actually a growing thing, and we're kind of, growing along with it. So thanks all for coming back. I realise that, some of you had anxieties about the last one, but not to worry. And Marco is always there and probably very open to collaboration if we really get stuck. So thanks very much, Marco, once again.
Yeah, you're welcome. And I'm happy to see so many of you here again, even though we had so much trouble last time. So I just want to ask really quickly if anybody has still got problems installing it. Do we have everyone with the software installed so we can just continue with the process of making the chronologies? Just somebody raise their hand if they still didn't manage to get the software done. If not, let's just do it.
Please don't remain silent and be lost for the whole workshop. Now's your opportunity.
Yeah. Okay, well, anyway, so one of the problems we were having last time was Martin's repository. I got him to fix that, so the installation process should be a little bit simpler now. If you're still having trouble, you can just email me or Martin. We'll figure out, maybe it's a bug in this code or something, but if not, we can still just try to guide you through the installation process. So let me share my screen. Give me a second. Just checking desktop. There you go. Can everybody see my screen? Perfect. So I will just really quickly repeat some of the stuff we did last time, which was showing you some of the code. So installation process, we got it through. It was kind of hard, but there it is. So in order to start using rPlum, we kind of need to call it, so the library. And then in order to run the example, we just run plum. We can actually delete this part. That's just to put everything in calendar years and not before present. So even if you just run that, that should be running. I won't run it now because we've seen these results. We also wanted to open this, show you the files that we need. So runs, here you go. So you're gonna have a folder called Plum Runs. We went through this last time, just a reminder, where you're gonna put all your cores. Every folder will be a different core with the name of the core. So you're gonna need a file with the name of the core. Ooh, oops, that's not what I wanted to do, but we can recall that. Give me a second. There you go. So it should be here. Yeah. So there should be a file called the same as your core folder. Yeah. So you can, I don't know if you can see that. So the file should be called exactly the same as the folder. That's just, and you put it in the plums folder. Once you have that, you can call it within R. So let's do that for core theme 1. As you can see, I have that file here in the folder, and it's called exactly the same as the folder.
So Marco, it's always a CSV file, is that correct?
Yes, it has to be an CSV file just because we could have it as Excel files, but R is very picky about Excel. So it's just a lot easier if you actually just use CSV files. Martin has implemented also TXT files if you have some of those, but again, it's preferable to use CSV files. So here, so we're gonna have this run, and I'm gonna really quickly change this file before the run. So when you say, because I'm pretty sure many of you are gonna be using this within Microsoft Excel. So one of the things you need to be careful of is the rounding process of Excel. And I'll show you why in a minute. Let me see if I can, again, always having trouble with it, opening these files. They take a little bit long, computer is slow. There you go. So let's say this is your file, your core file. And you decided to, and you had it in Excel, so you can see a lot of decimals, which it's a whole discussion how many decimals you need. But let's say you run that, and one of them, for example, this one, you round some of these to 0, right? Let's just put some zeros in there. That's something that could happen when you save from Microsoft Excel to CSV. And I'm gonna try to show you really quickly what that does, because it won't pick it up at the beginning. So let me open a terminal just to show you. Oh, it's finished. Let's just let it finish. This is a mistake I've seen a lot. When you have zeros in the uncertainty, let me stop that. Stop. Okay, so let's say I run it again with sim1. So as you see, it doesn't pick up any errors because the data is there, and the R language just recognizes a 0, no problem. But if you remember, I added a couple zeros, and let's see what that does. It's gonna take a couple minutes. So what happens here is you round it up, and maybe it was a very small number, and you say, well, it's a 0. So translate it into the model, that means you don't have any doubt that your activity at that level was, for example, 2.5, right? You have no doubt at all. Realistically, that's impossible because the machines we're measuring this with have some level of uncertainty. And the model will try to fit that, but it will actually fail. And this is what you get. And you will try to run it as many times as you want. You can increase the level of iterations, or you can do anything, and it will always fail. Because what's happening is you have the MCMC is basically trying many values to fit into our model, into the data, right? So we're trying millions and millions of models in order to kind of see the data we got. But if we are so sure of our data that we have no uncertainty, there's no model that's going to fit it, right? So that's what's happening within the MCMC. So always double check that there's no zeros in your uncertainty in Plum. There you go. There you go. Okay, so we've also seen how to add the data. So if we have only LED, we can use this format. Oh, sorry. No, this, if we have a proxy for the supported, given radium, given anything, you can add it into the next two columns, and the settings column gets moved to the left. So that's not a problem. You always need these columns. If you don't have that proxy, you can just use, I think this one, well, like this one. You can just use 1, 2, 3, 4, 5, 6 columns and your settings columns, right? So now let's start playing with the parameters. So as I was telling you last time, these green lines are our prior distributions. These prior distributions are just ones we use as default, and they were sort of set there first by Martin. This one in Bacon, that's a 20 years over centimeter. So there's 20 years for every centimeter. For lead, that seemed a little bit excessive, so we ended up cutting that in half. And it tends to work very well with bogs. So if you guys have a lake, that you probably need to change that. Defaults work well, but if you have more information, change these. Memory is a parameter you don't really need to move that much, because it's part of it, we call it like a, what's the name of it in English? In Spanish is estorbo, which is basically saying it's just there to help the model, but not really part of the inference. So I wouldn't change that much on this. You are sure what that would do. The influx is basically how much lead is coming into the sediment. Again, this is using Applebee's estimate of 50 becquerels over meter squared per year. And the supported, we put 10. Again, this was just done over seeing many cores that we took. And at the time we were doing these defaults, we got to see a lot of bit lines in the UK and around Europe. So pretty sure that would change around your area. So you could change that. But if you don't have any information, just leave that alone. Give me a second. My mouse is doing something. Not letting me move my mouse. There you go. So in order to change the accumulation, the prior distribution for the accumulation rate, you use two parameters, ACT mean and ACT shape. It's accumulation, the mean of the accumulation, and the shape of the accumulation. So let's see what happens here. So if we only look, let me try to show this bigger, because we only want the prior distribution here. So the default will give me a 10 here. If you see, this one is actually bigger, so it's reaching bigger numbers. So let me change that back to 10. So you see here. Here. So it's reaching lower numbers. So if we think our accumulation is bigger, we need to change that using accumulation mean. And I'll show you what accumulation shape does now. That basically is going to change the shape of this curve. So the mean will remain the same, but it will give weight to different parts of the curve. So let's say we want to change that to value like this, 0.1 and the strength 5. Oh, sorry. Here. So again, I did the wrong one. There you go. Oh, why is not changing something? This might be a bug in Martin's code. Let me run it. Well, one of the things here is I changed also the strength of the memory. Oh, sorry, this is what's happening. I'm changing the memory. So the mean of the memory now is 0.1 and the strength is 5. So by making this number bigger, we're actually giving it more weight to the mean in the memory. The same thing happens in accumulation rate. So let's try this in saying 50 in the accumulation rate here. So if you look at the plot of the accumulation rate, now 10 is basically the center of that curve, and it's almost like a normal distribution, right? The bigger we make that number, the more sure we are of the mean of the accumulation rate. So this is good when we have a lot of information about our core. But what happens if we run a core like this? We're so sure it's around, I don't know, let's give it a bad number. So let's say 50. No, something's going on here. Let's say 5. There you go. That one's going on.
Marco?
Yep.
There's a couple of questions in the chat.
Oh, sure.
If you don't mind.
No, that's perfect. The code is running, so it's perfect time for questions. Let me see.
I think the first question was about no probability of having an error of 0. Gabriel might be able to.
Yeah, that was it. I was more like just to know if I understood correctly. That's all.
Well, not really, because we're measuring this with machines that have an error already. So
no, as in like if you have 0 uncertainty, that means that you don't really have a probability of having that number when you try and and give it a distribution curve. If you have a 0 error, then you only have an infinitesimal sort of slice of probability, which tends to 0, right? Like tends to 0 probability. If you shrink your section low enough, that's what I was thinking, but maybe it's wrong.
Sorry,
you know
I'm
I mean?
not really following the.
Don't worry. I think I've got you anyway, but that's fine.
Okay. Sure. Then the other one was. Okay. We have to in the data points. We always use total let activity. So this one, so you'll have the density and then the total. And then if you have a proxy of the support activity, then Plum takes care of choosing what is the best support activity, and it will provide a posterior distribution, as you can see here. So this is our data for the support activity, and it provides a posterior distribution for what the support activity is. So here you go. So we have a chronology where we told it that we're so extremely sure that the accumulation rate at that site is around 5. So look at that. It's giving us exactly what we told it. A chronology that roughly goes around 5 all the time, right? Now, if you remember what last session I told you about these squares, well, these squares, this one is completely missing. And over here, the same. So that's pretty much an indication that something is wrong, right? Maybe we got it right around here, but we got everything else wrong. So we have to be careful about these prior distributions, right? So we need to give the model enough flexibility for it to know what's going on, because it's trying to merge both our prior knowledge with the data. And we have these sort of tools to indicate us, hey, something is wrong, right? So, because what's happening is the model is saying, oh, you're so sure? Well, I will ignore the data then. So again, this is how you change that, but be careful about it. So that's why we have this parameter always at 2 and the mean around 10. And that will give it enough flexibility. At least that's what we think. But if you guys have way better information, I would change the mean of the accumulation rate, but not the shape. The shape is something that most of the time should remain roughly the same. I mean, I wouldn't go over 5 or something like that. Just we need the model to give it enough flexibility. So the memory basically does similar things. Again, if you saw the plot before, we have it centered around and with mass probability around the whole interval. But if we look at this new one, we are so sure that there's no memory in the model, so we're gonna run it. Okay, any questions? I think Gabriel,
Yes.
question?
Yes. So I was wondering, in case you have, an influx of, say, like an oil spill or something that gives you a lot of lead coming into your system at some point, what's the best way to model that? Like, should you just have this big, wide range of mean, or can you have like a double sort of mean function, like a double peak function that models that, or what's the best way to go?
We actually, the gamma distribution is able to do those things you're describing, but the way they're programmed into the software are not done that way. But if there's double peaks like that, usually Plum picks them up. As long as the thing is, if you have, for example, a section that has a very different input of lead than another, what I would do there will be to put some sort of hiatus between those two sections, if you know where that break is. If not, then it becomes more difficult. But if it's only that you have like two sources and they get mixed they always get mixed, so you sort of still get that constant accumulation or a constant influx, then that shouldn't be a problem. Does that make sense?
Yeah, that makes sense. So it like as in the distribution is enough for it to say, okay, well, there's some probability of having a lot more accumulation, so it'll use that in some of its models, right?
Yeah, it's something that is actually quite nice here, important. That's why I haven't been looking for better priors for the influx. Is the model is actually very good at picking up the right influx. If you can see, our prior distribution for the influx in this run was 50, and it didn't give it too much flexibility. But look at that, even though there's 0 probability mass at the prior distribution, the model is picking up that the influx is actually like 3 times more than what we initially thought. So usually the influx is a variable that the model quickly picks up that something is different than the prior.
Yeah, I like what it does with the accumulation rate as well. It gets that big peak, even though, yeah, it's nice.
Yeah, that's usually, yeah. Well, this is actually pretty interesting because this distribution of the accumulation rate is the sum of all of it, right? So if you have some sort of section here, you could see the accumulation rate of just that little section, and the posterior distribution would look different. Actually, I'll show you that later today.
Okay.
But yeah, usually the model is really good at picking up that something is wrong.
Okay, that's good.
I mean, there's limits, right? You can, like, for example, last example, I forced basically the model to go through an accumulation of 5, and that's what it did. But then we have tools to see something is wrong. So it's just be critical when you're doing these models.
Yeah.
Basically
Thank you.
yeah. Okay. So this is how we play with the accumulations. Now let's add some radiocarbon data to this. I think for that, I'm going to use this core. Let me see if it's this one. Yeah, I think so. Yeah, so first let's start. Oh, sorry, my mouse always does this. There you go. So this is a core that we got for this example. I think there's nothing wrong with this one. Let me quickly check. This one probably didn't reach background, so let me check the other one. Here. Yeah, it's this one, the one I wanted to use.
Tun, did you have a question at all?
Sorry?
Oh, I think Atun had a question about the 51 sections in the chat, what it actually means.
Okay, sure. Where is the question? Oh, perfect. That's a good question. Okay, remember when I was explaining that Plum kind of separates the let part from the HDEV model, and for the HDEV model we're using the same as Bacon. Well, what Bacon does is creates sections, which we call Bacon sections, because it cuts the whole depth of the core in equal parts, and then it creates a model that is divided between those parts. So it's little lines going through all of those breaks. So those 51 sections are 50, it's basically saying it's gonna be breaking into 50 parts. So the bigger that number is, the more flexible the HDEV model is. So
Okay.
what I would recommend when you're working with this is try to, this is actually a good example. If you have a thickness of 0.5, I would actually tell the model that the Bacon sections should also be 0.5. Now we have to be careful with that because the smaller the Bacon sections, the more parameters we're going to deal with. And that also means the run is going to take longer, and we take the risk of never being able to converge because there's too many models and too little information. Remember when I was showing you in the plots in the presentation that sometimes very little data provides very big uncertainties and all of this? Well, numerically speaking, if you have very little data and a lot of parameters, the problem there is that it might never converge, or it might converge, but it will give you very strange results because there's more parameters to estimate than data points. So we need to balance these things out, right? So.
Thank you.
No, you're welcome. So give me a second, I have to go. So this one, let's run this one. So I have one file with the LED data here. Again, this is the format we've been seeing. And then this one, which is basically our Bacon file. So in order to put this into Plum, first of all, well, I put this because I did a run the other day, but you can just add that. So this is the coring date, and then how many data points from the bottom I want a supported activity. So I'm saying a sort of roughly rich background in the last 2 samples. So I'm putting a 2. Okay. So these 2 samples won't be part of the chronology. They'll only be used to estimate the support activity. Okay. In the cities, what does the value? Oh, there you go. It's exactly what I was saying. So it is these 2 values. So if we change that to just 1, it would only take this value as support activity, and it will try to infer it. That's what I would do sometimes, but this one has very little data, so I'll keep those 2. Now, there's a bug right now with Plum and bacon and the mix between bacon. So these sections of the reservoir effect need to be deleted before running them into Plum. And the other thing here is we're missing the, if you can see, oh, give me a second, my mouse is playing around. If you see here, I don't have a surface state. And I explained that last session, we don't have a surface date because our surface date is already here. So if you put it here, that's not a problem, but numerically, it will kind of just, Plum will try to use the data, even though it's not real information, right? So it will give you a result, and it probably will be right, but it's just best not just to keep it away. That's the calibration curve. So these are radiocarbon measurements. So we somebody asked what CC means. So I'm explaining that CC is the calibration curve, and we want to use the third calibration curve, which I believe is the south calibration curve. So that's what we're using. So if we have the cesium here, we can add it here as well, and we'll use a calibration curve of 0, I believe. So that's how we put all that data in.
That's the same with things like, you know, tephras that you have a precise date for. You don't
Exactly.
calibrate them, so you put a 0 in the CC column.
I think it's number 4 rather than 0.
Oh, is it number 4 for tephras? Okay.
Yeah, I think Bacon used the age. You know, when you know the age, calendar age, you can put number 4. Is it right, Marco? I checked yesterday. Yeah.
I can look it up and check. To be honest, I've never really used tephras in the course I've been using, but I can check. Maybe there's a special one for tephras. But for calendar dates, I believe it's 0. That's what we've been using for a long time. Let me check really quickly. I do have one. No, not this one. I can check. Maybe I'm wrong. This one. Of course, this one should have the radiocarbon. No. Oh, I know which one. Yeah, this one surely has a. There you go. Yeah, we use 0. So this is an example of a core with cesium and radiocarbon. So cesium will be, the age will be put in before present terms, the depth, error, and calibration curve 0.
That means it's different than Bacon. Can I share my screen to show you?
Sure.
Yep.
Sure. Yeah.
How I share my screen now? Okay.
Give me a second. I need to stop sharing. There you go.
Okay. Let me do the sharing. Okay. Share. If I go to, hang on, just bear with me. rPlum. If I go to document, I go to Bacon. Okay. And here, the setting of Bacon, here you can see the constant is CC number 4. Yeah.
Okay.
Yeah.
Okay. I'll have a look and I'll give you what's the difference there. I believe it's the same because they shared the same code on that part. But I'm gonna check. Maybe something changed.
Okay, I stop sharing. Okay. Yeah.
Second, I actually pull out the manual really quickly to check this point.
Oh, Marco, I just had a look in the manual and it says, I've just pasted it in the chat.
There you go.
And it says CC4 is an alternative calibration curve. Things that shouldn't be calibrated should be CC0.
Yeah. Yeah, so 4 could be the constant if you give it a file with a constant.
So if you've got a calibration curve for a particular location or something like that.
Yep. Yeah, that sometimes happens. Okay, that's the mystery there. So, so yeah, once we got all that data in there, we're gonna run it with the name of the file, of the folder, and then the name of the core, and actually the name of the radiocarbon file. For some cases, for some strange reason, sometimes we need to add the CSV, the .csv, at least for Macs. I've seen that that's one of the problems. If I don't do that, this is an error that, oh, hold on. Okay, there you go. See, it gives me an error. It says that such file doesn't exist. If that happens, sometimes you can just add the .csv and it will find it. All right. That's one of the common problems there. So we can see all the radiocarbon data here on the left, and the lead data over here. And we can run that. Any questions while this is running? Oh.
Yeah, Marco, I've got a question. It's Christina here. So this is one of my cores, actually. And we don't really know why there appears to be a reservoir effect.
Okay.
So, yeah, when you don't really know the reason behind it, how can you really ignore them, I suppose? Because if there was a genuine one, then you would have to somehow take that into account for the remaining radiocarbon dates.
So only one data point appears to have some reservoir effect. That's what you mean?
Yeah, and we're actually waiting on another 2 dates within that zone to try and figure out.
Okay, what usually happens is there's outliers in radiocarbon. It's quite a common problem. Actually, we say that almost every 10th sample would probably, every 10 samples would have one outlier. That's why there was a whole discussion about it. So I believe bChrome has some sort of methodology to fix them, so to include them into the chronologies, and Oxcal as well. But in Bacon and Plum, we, instead of using that, we use the T distribution, instead of using a normal distribution for radiocarbon dates, we use a T distribution. What that does is basically give a little bit more weight to the tails, and that allows us to don't get affected by outliers. So you could actually still include them into your chronologies, and most of the time it will be okay. I don't know if that answers the question.
Yeah, thank you.
Perfect. Okay, so this is finishing up. Let's make it big. So as you saw at the beginning, Plum decided to change the accumulation rate by looking at the radiocarbon dates. That's what it did here. What else? We only had 2 data points here, so that's what it's doing. For some reason, this one is looking like a radiocarbon date, even though it wasn't, was it? Give me a second, I'm gonna learn runs.
Is that the top of the core date?
Sorry?
Maybe that's the top of the core.
It could be, yeah. Give me a second. Did I put the top of the core?
I think we put it in the settings.
I know what happened. I forgot to save the file when I deleted these things, but it did run, so Martin got that fixed. Perfect. So yeah, you can add reservoir effects here now. This is great. So yeah, that's the chronology. For some reason, this one it's doing that. I'll check it out later. For some reason, it's probably not in agreement with the lead, so it's deciding to use the lead instead of that radiocarbon, but it's choosing all the other radiocarbons. Okay. So it's as easy as that. You just add two files, your lead file and your radiocarbon, or other dates file, which is the name we have it, other dates. So one other thing here is, one of the variables here is thick. Remember when somebody was asking me about the sections? This is the way to change those sections. So thick defines how thick the bacon sections are. By default, Plum has those thickness set to 1 centimeter. So there will be 1 centimeter, one section every centimeter. That sometimes is difficult because you will have a core that goes way down because of your radiocarbon dates. You can make that bigger. For example, let's change that to the default in bacon, which is usually 5. Something got wrong. Oh, I'm using the different one here. Sorry. So there you go. Let me remove this here. So if you saw, it was asking me, sorry, I went too fast there. It was asking me if I wanted to use 17 sections, which is way smaller than what we had last time. So the result of that is we have a much faster model. And you could use this to make quick estimates to see if something is wrong. So you don't have to wait hours. And the model still is coming out okay. These errors, I'm not sure, but I mean this is actually C code. So I'm pretty sure Martin got a little typo somewhere. So don't worry about those. Okay, what happens if you erase your plot? Just for some reason you deleted that plot. So you could run, and you deleted everything. You close your R session. One of the things you can do is actually copy the same code you did and say run equals false, which pretty much tells Plum and even Bacon not to run the MCMC, that just take the data from the files and show me what I did last time. It's going to ask you a couple questions again. You just say, yeah. And there's some errors here. Okay, let me make a note. This is an error that wasn't happening. Okay, let's run it really quickly, just to continue the session. That will be the way to recover a run if you want to analyze it further. Some reason it's not working, so give me a second. I'm going to it doesn't take that long anyway. There you go. So let's say you lost that plot, didn't save it or something like that. What you can do is use the hdef function and it will redo everything. It will give you the exact same plot. Okay. You will recalculate everything that needs to be recalculated.
I had a question.
Yeah.
Okay. In the last run, the result showing the delta R is 0. Does mean they have no delta R or reservoir in building the model. Is that right?
You mean the file?
Yeah. At the in the file at the end, you open, then you have delta R is delta R 0 here. Does
Yeah.
mean, yeah.
That means there's no reservoir effect.
Okay, if they have the number, that means they use the reservoir. Is it right?
Yeah. Yeah.
Okay.
Yeah, but you need to estimate that beforehand before putting it here. So if you have an estimate for the reservoir effect, you put it there.
Oh, that's one is the input file or the result file, the output file.
Yep. Yeah, it's the input file. So you do need an estimate of the reservoir effect. If you don't have one, I'll show you later how to get one
Okay.
using Plum. But for now, that's the way this one works.
Okay, thanks. Yep.
Yeah. So any questions up to this point? Because I'm gonna start doing something that is not, well, it is part of the model and it's part of the chronologies, but it's not exactly to do with the chronologies like this.
I have a quick question
Yep.
about so in the original file, you had this first line, which is like surface, like it's in the CSV file for the carbon dating and other dates. There was this surface. I was just wondering what that was, and what it says surface -59 for the age, and then error 30.
I'll show you. Well, I'll show you both files so you get it. So this one I prepared for showing you today, but this one is one that I didn't get. So basically, the surface date is something that Bacon users use to add a date and to make the core reach the surface.
Okay.
Okay.
So it's like a the synthetic sort of thing? Or,
yeah.
Okay.
It's a way to put the coring date, basically.
Yeah. Cool.
Into Bacon, but because radiocarbon dates sort of live by themselves, they don't need a coring date. You can just take them and they'll give you an estimate of the age, regardless of whenever you take them. So it's not really needed to create a chronology. So this was sort of the artificial way to extend the chronology all the way to the surface using radiocarbon dates. But because Plum and LED do require the coring date, because that's how we know where they come from, what date they are. We actually only estimate how old they are on relationship with when we took them, the samples.
Yep.
So we need that in Plum. So that's why I always make an emphasis of you need to delete that surface date from your Bacon files, because people that use Bacon will have that in their files.
Oh, okay. Right.
Yeah. So that's why this one doesn't have it and this one does. Because I didn't prepare this one and that one was prepared. Okay?
Perfect.
Oh, yeah.
Just, are you going to explain what those T.A or T.B, or have you already explained what they are? Because I didn't quite catch what those
This one's.
Yeah, those TA and TB, yeah.
Okay, I didn't want to go into detail about those.
Sorry.
No, it's perfectly fine. Okay, remember I was just saying that for outliers, Bacon used the T model instead of a normal distribution.
Yes. Okay.
To correct outliers. Well, these are the parameters for the T model. Okay, these actually are the defaults for the T model. So the person who created this file really knows what they're doing with Bacon, because this is what Bacon would read. So Bacon would read the calibration curve, check for reservoir effect, and then check if you want to change the distribution of your radiocarbon dates.
Right.
So they're leaving it as default because these are the default for bacon. But if you wanted to change them, this is how you do it. So instead of, for example, if you wanted to give, for example, more weight to the tails because you think it's way more likely that that date is an outlier, you will change these variables. I believe you will make B bigger. But the problem with playing with these ones is that you will end up with something that might not look like a normal distribution, or you may end up with something that is too weighted one side, or it is probably too narrow. You need to have a good knowledge of how the t distribution would look after you change this. Because if you don't, you have to remember that your radiocarbon dates have to go through calibration, and the calibration curve is all around. So the finished distribution will look very messy. So there's no way to predict if you change these parameters a lot or not. So that's why we always suggest to never change that unless you're sure you know what you're doing.
Noted. Thank you.
Can I answer on that question?
Yeah.
If you change this number, you can use that one as something you ask to remove outlier or put the outlier is lower weight.
Yes, you could. You can
Okay.
look at the parameters of the t distribution that will make the distribution less like a normal distribution, but more like a flat thing. That will give it more weight to the ends, or even if you wanted to move it to one side, you could. But again, you need a very good knowledge of what the end distribution would be if you move those parameters. And when you write your paper, you need to justify those parameters. Like you really justify them. Like you really say, I was very sure that my radiocarbon date had a problem and I needed to weight it more to the left or more to the right, or I was extremely sure that this was younger and you need to prove, right?
Okay, thank you.
So yeah, again, these parameters are there for changing, giving more weight or not to certain radiocarbon dates, but you need to be careful and you need to really justify what you're doing with those parameters. Because sadly, we don't have a way to actually show those parameters on the outputs, just like we do with everything else, right? So we have a way to see the prior distributions of everything, but for those ones we don't, because it's too much information at once, and the model nobody really changed those parameters unless they really know what they would do.
Okay, thank you.
You're welcome.
Marco, can I ask a question? I know a few of the people here have to leave at some point. Would you have a moment to show us the outputs of the model? So people that are thinking, okay, I've got to this point with rPlum, but where do I see the ages for all of the sample depths that I might want to plot in some other thing? Just so they can see exactly how they would use the output files to plot their own proxies or whatnot, if that's possible.
Yeah, give me a second.
Thank you.
Sorry, I got a message there. There you go. So you're gonna go to the same folder where you put all your files, all your input files, and you're gonna see a lot of files there. Let me make this there. Let me make it bigger so you can see. So if you go to this place in the folder, you will see the original files you put in there. So this one and this one are those files. But then you will see a settings file. If you open that settings file, you will see all the settings you put into the model. So your minimal depth, your maximum depth, by how long it was every date that you're gonna get in the file. Depth file is if you wanted some depths, some, how you call it, some special depths, and you want the age of those special depths, you will make a file, put it in there. because we didn't do that. It's saying false. The accumulation rates of the priors, calibration curves that you use. If you wanted regular dates of post-bomb, here is where we're gonna see the T parameters of the parameters for the T distributions. If you wanted reservoir effects, everything will be here. All the settings for recreating that plot will be there. This file, the .plum file and the .out file, I wouldn't worry about them. They're internal for Plum and Bacon. These are the files where all the data is stored, but it's encrypted and R will decrypt it for you. You can actually open them and you can actually see what is in there. Let me see if this program opens. There you go. It's just a little bit slow. There you go. So you will see here that that file only contains the 2 data points that we use for the supported activity, right? So again, it's information that you already have somewhere else, but it's the way the program needs it. If you get this .out, I won't do it because this one can take hours to open because it has every iteration out there. Like everything that Bacon did, it's in there. So you could open it, but it will take a while for you to see it. So it will be, and it will be just numbers. It will be all the numbers that the method calculated. And that's why it always weights a lot. Let me check how much it weights this one. So it does weigh 3 megabytes of just numbers. So you can imagine that it's gonna take a little bit long to display on your screen. Same thing with plum.out. It will be just this one we might be able to see, which is less data. Let's leave it there for a minute. Hopefully it will open. There you go. This is basically all the data points that we needed. Actually, this is, if I remember right, the first one will be the influx and the second one will be the support activity. And it's every single iteration that the method did. So it's quite a big file. So if you, for some reason, need that, it's there. It's those 2 files. This one is specifically for Plum. This one is specifically for Bacon. For the Bacon part of the method. If you want the dates, this is where they are. A file named the same as your core, but with a number and ages. The little number is the Bacon sections that you use. So if you, this is the first one we did, it did 83 sections, and this is the ages with the minimum and maximum, medium, and mean of every centimeter, all the way to 83. We've got another run with less data, with less Bacon sections. And that's this one. And as you can see, it's still there. So at depth 0, we're very sure it's that date. Then we keep going and we got the intervals and everything. And if you want the plot in a PDF, that's where you find it here as well. For some reason you lost or something, that file, that run or something, it's gonna be there. This is the last one we did. There you go. So everything you need is gonna be in the same folder where you put the input files. Okay. Any other question?
Thanks very much, Marco. Did you want to take a break at all?
Sure. Let's take a little break. What about 10 minutes?
Sounds great. Okay, thanks very much. We'll see you back in 10 minutes.
That's good. I'll see you in 10 minutes. How do I stop sharing my screen? I don't see the buttons anymore. Oh, there you go. You let me know whenever we continue, okay?
Sure. Hopefully most people are back. Yep, we've got a couple of thumbs up here, so I think we're right to go, Marco.
Okay, perfect.
Thanks very much. Oh, there's already a question for you in the chat
Okay, let me see.
from Asika.
You get any other days like you can use them. Okay, I don't really get the question. Okay.
Yes, Marco, I'm sorry. Yeah. So I've got cesium dates, sorry, plutonium dates with like 210 dates. So I'm just wondering, like when I plot them with bacon, because I can't see any other dates in the Macquarie Island core except like 210 dates. So I'm wondering, do I have to include plutonium dates when I'm plotting them in bacon, like with bacon?
Well, if you have your, if you use bacon, I'm guessing what you did was model your lead dates.
Yes, I've got like
bacon.
Sorry, what?
Right. So you first model your lead dates and then
Okay.
put all of those into bacon, right?
Okay.
No. Is that what you're doing?
So I'm a bit confused because I've got like 210 dates with like just like few plutonium dates. So I wonder, like when I'm like making the Excel sheet, do I have to include my plutonium dates in the like lead 210 data sheet, or do I have to just ignore them?
Do you mean when put them into bacon?
Yes, when making the bacon model, like when I'm making the trying the,
Yeah.
do I have to include them or just ignore?
No, what you do is I'll show you really quickly. So just like you did with your radiocarbon dates, this is
Okay.
an example. You will put them here, but for example, you see this one, that will be, for example, this probably is not a cesium date. Oh, I'll get a file with a cesium date.
Okay.
Give me a second here, and I'll show you. Here you go. So you have your lead file, as we were seeing, and then you have your older dates file.
Okay.
And as you can see, this one, it has a cesium date.
Yeah, just one. Yeah.
Yeah, you will put it with before present format in the
Okay.
date. So -13, that'll be 1963, I think. And a small error, just because you will have very small errors. The depth, and for the calibration curve, you will choose 0.
Okay.
That's how you put your cesium dates here.
Okay, so I put them with the other carbon 14 dates, right?
Yeah, that's correct.
All right. Yeah, thank you.
You're welcome. Ah, okay, something happened there. I need to reinstall my Plum for some reason. Computer decided that it doesn't want Plum anymore. Just give me a second. So any other questions? What I'll do from now on, I'm going to create one of the models, and I'm going to use that to start showing you some of the other plots that Bacon and Plum do, which is the plots of the accumulation rates. This is actually quite good for when you want to do the studies for your accumulation rates. So let me run this model really quickly. Okay. Oh, okay. This is a common error. I'll show you. It's good that this error came out. Good. So when you see that error, but files with NAs, what you're going to do is go to your folder, look for that file. Delete all of this. We don't need that anymore. You're going to look for your file. As you can see, it looks normal. And then if we open it with a text file, a text editor, sorry. Oh, there you go. You should be able to see blank spaces. You delete those, and that should work to delete that error. Let's see if that works. If not, okay. I don't know what's happening then. Box everywhere. That should be okay. What's going on? Let me just run the default core so we have something to continue with. It's going to take a couple of minutes. Any other questions up to this point? No? Okay, then just wait a couple of seconds so we can continue. Sorry with this little.
So Marco, maybe while we've got a minute, could you explain what the purpose of the next sections that you're going to go through are? So you're saying that we're going to plot accumulation rates. So
Yeah.
how would we use that or why would we need to do that in a practical sense?
Well, if you're going to study how the accumulation rates change, these plots actually show you that they're in a graphical model, in a graphical way, not just the numbers. You could actually see, and not just that, one of the beauty of them is that you will see the uncertainties related to that, to the accumulation rates.
Okay.
So you not only get the uncertainties on the h-axis, you're going to get them in the accumulation rate. So when you talk about the accumulation rate, you can actually give an interval.
Oh, that's great, because yeah, a lot of the stuff that well, various colleagues and I do is work with things like charcoal accumulation rates, and of course they depend entirely on the age depth model. So being able to incorporate that kind of error into our quantification would be a really useful thing.
Yeah, and it's been implemented in Bacon for ages, but people just don't. For some reason, people don't really use it.
I've never used it.
Very few people know of its existence even.
I didn't know before this.
Yeah, and it's already in Bacon for ages, and it's just one of the products of doing Bayesian methodologies, because everything is part of a model, so everything has uncertainty. So, and we can measure it, and the accumulation rate, as I was mentioning, is calculated at every Bacon section.
Yeah.
So we can actually take that and extract the uncertainty related to that. So
can I just say that I think it's the reason people don't use it, because we've attempted to use it, is because it's not that well documented. Like, it's hard. We've tried using it. The documentation around it in the Bacon manual is really hard to understand. So,
yeah, I get that.
Yeah, so that's we've had a few failed attempts at trying to use it, actually. Yeah.
Well, perfect. We can see how it's done now. So, okay, so let's say you wanted to check the accumulation rate at certain depth. So what you're going to do is pretty much use the accumulation rate dot depth function, and you give it the depth you want. So if I run this, okay, computer, do something here. There you go. It's going to give you every iteration of the model, right? It's going to give you everything. So there you go. I'm going to save it into an object in R, and I'm going to use the head option. That's just going to give you the first couple of numbers. So we can see that it's around 2. If we want the mean and the variance, we can calculate them. We can actually use the function. I think this one is much better. Summary. And that's going to give us a lot of information about those, about the accumulation rate at the depth of 10 centimeters. But if we wanted to plot it, this is where it becomes tricky, and that's why I understand many people don't using it. you will need to use two functions, which is the density function and then the plot function. So you pretty much create the density using the numbers we calculated and then plot that. Oh, give me a second. There we go. There. So the accumulation rate at depth 10, it's between 2 and 2.5 with its uncertainty. So we can see that now we have a posterior distribution. We can do that for any depth. This one is for the depth of 25. You can see it's a lot different now. It's not symmetrical anymore. So yeah, that's how you use that little function there, just to get for one single depth. But we don't really want that at depths. We sometimes want that at ages, right? So we can do that the same with ages. So instead of that depth, we use age. So an age of 300. It's going to take longer because it's going to calculate the age depth model and then do the numbers. We can do the summary here to calculate. Oh, something went wrong there. Oh, I know what's going on. 3 centimeters, just because plum doesn't reach 300. There you go. So we call it, we got it around that age. Let's plot it. Now we get an accumulation rate for 3 BC before present. Sorry about that. There you go. If we want histogram instead of a density, we can also do that. If we want that instead of years over centimeter, and we want it for centimeter over years, we're just going to use this little, oh, my mouse is up again. Here you go. Centimeter year equals true, and that's going to change the scale of the accumulation rate. And we can get a density as well. So this is a good example because look at that. We actually got a very nice curve of distribution and then a little bit of bumps from here. So the model is playing with something over there, but it's saying it's not significant. So if we want a specific ages or specific dates, this is how we do it. We use the accumulation rate dot density or age, either one. Let's say we want the whole model to plot the whole thing. We don't only want one depth. We use this one, which is accumulation rate dot depth dot ghost. We want to change the scale of the accumulation rate, and then we just give it a limit just to see it much better. And this is it. So this is how the accumulation rate changed over the depth of the core. So it's quite nice. We can see some pattern going here and then changing over here. And the nice thing is that we have these uncertainty bars that help us where we can see that there's a lot more uncertainty on the deepest part of the core, which is exactly what we thought anyway. There's a question, I think. Yes, it is using the last run that you use. That's why it's important to do your run and then do these things. And if you don't want to do that, if you already have your run saved, you will say run equals false. Hopefully it will work. Yeah, there you go. It worked. So if you already closed your R, you can just use run equals false and it will do it. What else? You can actually change which part of the let's see what's going on here. It's gonna work. No, something happened here. Give me a second. For some reason it's not liking the run false function. So let's do it again. Okay, sure. Give me a second. Any questions up to this point? We are almost finished, actually. I just wanted to show you these plots and plots for the ages, which is basically the same thing. Accumulation rates over the ages and not the depths. Any questions?
One from me again. Is there somewhere where we can, where there's an output file with this information, Marco? If we
That's a good question. I don't think Martin has implemented files for these functions, but I will tell him to do it.
Okay, yeah.
Files for, yeah.
Yeah, would just be maybe useful if we wanted to, you know, for example, if we were looking at things like, is a charcoal peak in our record a significant charcoal peak or not? And depending on the accumulation rate and the uncertainties, it could be or it may not be. So it might be useful for testing certain paleoecological questions like that to have the output file.
Okay, yeah, but I'll ask Martin about it. I had the same feeling that those things were important, but he just never implemented it, and he's calculating them anyway. So
okay,
just
yeah.
making a line saying put them somewhere, right? So it should be easy to implement. I'll tell him whenever I give him my reports of more bugs that I found.
Thank you.
Yeah, it is great because this thing keeps improving every day with all the bugs we find. Just a couple seconds.
And I think that's something as well. Like it's Janelle pointed out that she didn't find the manual very helpful, but I suppose the thing's developing all the time, so it's kind of hard to keep up with the developments and writing a manual at the same time.
Yeah, no, it is a long process. For example, for rPlum, I still haven't got around making a whole manual about it because it is just time consuming, and rather sometimes just there's more urgent things like fixing these little bugs, you know what I mean?
Yeah.
Because you want it to be useful for as many people as you can.
Yeah, for sure.
So there you go. So we're back to this plot. So if you want just certain part of it, you can plot it here. Again, there's a little bug there, but you can plot the uncertainties there. If you want the ages, you just change depth for age, and again, ghost. It's ghost plots because they kind of look like ghosts, that they are very light grades. So yeah, this one is calculating. Give it a second. This one takes a lot longer because we're dealing with ages. So it needs to pair the accumulation rate with its appropriate age, and it needs a lot more calculations, but I mean, it's the same. There you go. So now we have a nice model that goes on the age axis instead of the depth. So we can talk about ages and how the accumulation rate change over the ages. So we have a peak here that is very significant. So these plots, yeah.
And the different colored lines, are they mean and median or a running mean or?
Yeah, mean, medium. I believe the blue is mean, the red is medium, and the gray is the uncertainty bars.
Great, thanks.
Right. Any other questions? I think that'll be all for this part of the section of the talk where I explain these sort of things. But I think what we're gonna do next is show you the rPlum part, the one about Python, where you can estimate the reservoir effects. And after that, what I would recommend for next session is for everyone to bring a core, and we can break up in rooms and we can run these things with your own course. And if there's any questions, any problems that we're encountering as we go, we'll talk about them there. So I don't know if anybody has any questions or any suggestions on anything else. If you want to see anything, go explore a little bit further, or should we just go into Python right away? No questions? Okay. So this is, I'm gonna close this part. So you guys talk a lot about reservoir effects, so I thought it was important to show you this, even though, sorry. Oh, let me open that code again. Here, do you mean, yeah. Basically what I'm saying is show me between show me the accumulation rates from 0 to 40. Somebody's asking what that line is in the accumulation goes, where I said act lim. I'm just saying plot only from 0 to 40. If I don't do that, sometimes it goes shooting, because one of the iterations might try something crazy, so it just goes bonkers. So it's just a way to limit it. You can change that to anything. It's the same here, accumulation limit from 0 to 5.
So it's their axis limits basically on the graph.
Yeah, exactly.
Yeah.
Yeah, so if you wanted that to 15, for example, it's just how we want the plot. Okay, so for reservoir effect, I created this other little thing. I'm going to show you how it looks. Here it is. So this is that core we didn't run over there because it had reservoir effects. You can see there's some radiocarbon dates here that are very far away from the chronology. And that's because there's a reservoir effect. So you can see that we have the same plots, the lookup object, the accumulation rate, the memory, the influx, and the supported. But we have this other plot here, which is the reservoir effect. So what this methodology is doing, I'm not guessing initially anything about the reservoir effect. I'm going to show you the file. So here it is. So there's no information about the reservoir effect at all. What this method does is actually infer the reservoir effect given all the other data. So we have let here, let data, just the same format as rPlum. And we have, I believe, 2 points that are not radiocarbon dates. So we can trust them to not have reservoir effect. At least that's what we think. So what rPlum does is create a chronology and start moving the reservoir effect until it makes sense and all the radiocarbon makes sense with everything else. So how do we play with that? Well, it's quite easy. You just need to download Python. I believe I did. Give me a second. Oh, here you go. I did a script to show you. So this is basically, again, how it looks. It takes a minute. There you go. So you're going to download rPlum for, you're going to download this repository from my GitHub. You go into code, you're going to download it as a zip file, and you're just going to open it somewhere. Once it's open, where did it open it? Here you go. You're going to find a rPlum.py file, and you're just going to put that in your home folder. There you go. I need to replace it because I had it there already. Let's do it the way it is. And then in your Python terminal, or if you're in Windows, or just type Python into the terminal on Mac, you're gonna type that. And you're basically just gonna do the same we did before. We're gonna call it, which is import rPlum, which is basically almost the same as R. Once that's done, it's gonna take a minute. You're gonna create an object. This is Python. So you're gonna create an object called rPlum.plum with the name of the folder where everything is. I told it that the thickness I wanted it was of 0.5 centimeters. I'm probably gonna change that to a little bit bigger to make it faster. How many support activity, the mean, all the same data, and then you're gonna tell it if you want to play with the reservoir effect, and you're gonna say yes, so true. Prior distributions for the reservoir effect, I'm giving it 2000 because it was quite a big reservoir effect. And the reservoir effect prior uncertainty, so about 500 years. So I'm giving it just a lot of space to play around. So I create that object. If everything went right, it's gonna load me the LED data, the calendar dates that are not radiocarbon, and the radiocarbon dates. That's how this should look. So all the LED data accompanied by the calendar dates and the radiocarbon data. Once that's done, you're just gonna run it. So with that function, the same name as before, .run_plum. And that's just gonna run for a couple minutes. Once that's done, you should go to your documents folder, your PyPlum folder, the folder of your core, and you're gonna find something looking like this. The next thing I'm gonna program in is a way to actually see the radiocarbon dates once they're corrected, but it's something I haven't programmed into the software, but it's coming. So if you have no idea what your reservoir effects are, you can use this software to do that. I don't know if you guys have any questions on that.
Yeah, Marco, there's one in the chat. I think a few people like myself don't have Python installed, so we're a bit behind. But Kwan suggested maybe having just a few written points about how we would do it if we want to do it a bit later in our own time or something like that.
Yeah, so. Yeah, sure. What I'll do for next session is I'll try to comment this file.
I think today's the last session.
Is it? Oh yeah, I think it is.
Yeah.
Well, anyway, yeah, I think it is. Sorry, I'm.
That's all right. That's all right.
I've been having too much fun.
Yeah, but maybe if you could
I'll document.
Provide us with this little bit of script and a couple of comments, and just so we know what to do in our spare time.
Sure.
Oh, people want more sessions. They love you, Marco.
Oh, yeah. Oh no, that's great. I think there was one more schedule. Oh no, sorry, no, there's not. Yeah, we can talk about it with you and Larissa. I don't think next week I'm available, but we can leave it for another date.
Yeah, I think I'm getting messages from Larissa here, so she's got to talk to Kabar and things like that.
I'm here.
Yeah.
Yes. We have talked to Kabar to see if we can make a bigger workshop, but yeah, something still on plans.
Okay. Yeah. Look, we can have just a little extra session where.
Anything that you think might be useful, Marco, also we can put in the OneDrive folder, scripts and stuff like that people can have a go by themselves.
Yeah, I'll comment this. I'll send it to you so you can put it in the OneDrive. I think
Yeah.
all the materials we use are in the OneDrive. So if people want to replicate anything, they should be able to. Everything is in there. So, and actually, the GitHub repository actually already gives a brief description on how to use the method. Really, if you go here before you download, it's an introduction of it, a little bit of warnings, what you need and what you need to install. It's there, and just a brief description of how the files need to look like. And this is actually a tutorial on how to run it. So again, load, core name, core and rPlum, and then all the settings with their descriptions. So I'll still make this file a little bit more populated with comments to describe everything, because the point of this one is to actually show you how the reservoir effect can be estimated by Plum itself. You don't need an extra step to estimate that. But yeah, I'll comment that one and just send it to you guys. I don't know.
Yep.
If that help. Any other questions, you can just email me. I'm always happy to answer some questions. And if there's a very difficult thing, we can just set it as a collaboration, and I can, if there's something that is just not working with anything else, I'll program something that will try to make it work. That's what we did in a couple of papers. Yeah.
That's great. Yeah, so we'll try and organise a follow-up workshop with you. You know, maybe in a few weeks' time, something like that, when you're available.
Yeah.
Yeah, then people can have a little play with their own data a bit more, and yeah, try and run some models.
Yeah.
Can I have a question?
Mm-hmm.
Yeah. About the reservoir effect, have you, at the moment, you mentioned about the constant reservoir effect. Do you have any think about in the future you do something to have a changing in the reservoir effect through time? For example, you know, like one depth you have one the reservoir A, but depth B you have reservoir B, and depth C they have a reservoir C. Have you think about that?
Yes, but it becomes a problem of availability of data. So this method works because there's other dating points. For example, I don't know if you can still see here, but there's, let me see if I can make this bigger. I'll open it right there. So this thing, oh, there you go. So this green lines, even though they just look like green lines, they're actually, I believe they were tephras, if I remember right, the person who told me. So there's a tephra there, another tephra there, and the lead part is in this part over here. So there's a lot of information that is able to fix that reservoir effect, right? So if we have more sections for the reservoir effect, it is possible, as long as within those sections you have information to fix it, right?
Okay.
Yeah, or maybe you can say, well, the reservoir effect is changing over time, and there's a linear, I don't know, a linear increase on the reservoir effect as we go lower. Then we can program that in, and that could work. I mean, it will require some programming and all that, but you see what I mean? We need some sort of information.
Yeah. What I do at the moment, I use the upscale, right? And I change the upscale calibration curve by including the reservoir, the variable reservoir in the, you know, like incorporate into the calibration curve, and then I can run it. But it's great if I can see something, you know, can be done with the bacon or rPlum.
Yeah, look, if you want, send me an email. We can look at the details, because it sounds like something we can actually work together on, like to actually implement that idea into the method. Like the thing you do manually, maybe we can incorporate it automatically in the bacon model. So if you want, send me an email and we can work on it.
Yeah, I can send you some information and then we can, you know, think about, yeah.
Yeah, sounds good. Sounds like
Okay.
Marco, do you want to put your email in the chat?
I'll do that. Oh, quite an easy email. There you go. So it's my last name and at cmat.mx. So yeah, anything you guys, if you're having difficulties with the program or more challenging course and things like that, this one I used way less sections, so you can see it's a little bit more square, but it's giving similar results. So that's why you need to be careful with the number of sections. So yeah, I don't know if you guys have any other questions. I think we're very nearly at the time.
With the model you last showed, is there some parameter we can change to affect how many kind of bends and angles it has in it? Sometimes we get very bendy kind of age depth models that become quite unrealistic.
That's exactly the thick parameter, how thick the bacon sections are.
Mm-hmm.
Like I did it like this because, like, for example, this one I show first. So this one looks very nice. It looks very much like bacon does all the time. But it's because it's using 151 sections and it took an hour and a half to run. So we can't do that here. So that's why I did a lot less iterations. That's why I was saying you need to be careful with the number of parameters and your data and the data available, because it can take a lot of computer time. So just to show you how it ran, I created this one. It has only 16 sections. So a tenth of the resolution. So it's basically the resolution of the model. So that thick parameter, which is how thick the bacon sections are, is basically the resolution of the model. So you can make that very, very, very small, but you will theoretically get a high resolution model, but you need a lot of data for that to work, and it will take ages to compute, right? So that's why I always say you need to be careful with how many parameters you put into the model. So how big or small you make this parameter here thick. And that's the same it's called the same in R. So if you go here, look, if I run this, we've seen this code run many times. It takes a couple of minutes. But what happens if I make thick, I don't know, instead of 1.5? Look at that. It's writing. It's going to run with 11 sections instead of 51. And it should finish in a couple of seconds. I mean, it's going to take way less than what it did before. I mean, it's still going to take, there you go, it's finished, which is a lot less. But if we see the result, look at it, it's going to look squarey. So yeah, the default is 1 just because it's the number we think gives a good resolution for many cores. But if you guys are working with samples that have 0.1 thickness, then you probably need to change that. And again, think about how much data you're putting into the model and if it's realistic to get a model with that resolution. So see, it just became very squarey. So yeah. I don't know if you guys have another question.
Anyone?
No?
Hi, Marco, may I ask a quick question?
Sure.
You know, in these panels on top of the model,
Yep.
what is that you really don't want to see there? Like, you know, like, is there any visual warnings that the model is not what it should be just by visually looking at these panels?
There's only one. If the memory gets stuck on 1, like literally you can't see any gray here and only see like a tall line in 1, that rPlum probably is wrong. And that usually looks like a straight line here. Other than that, this one is more, the one here in the plot is way more informative. Let me show you. So you see that square here and how the distance from the ghost is.
Mm.
That's a bad sign. That's a really bad sign.
Why is that?
Because it's saying the method is not guessing the data right?
Oh, I see.
Even though it's a good run. And the reason because it's a good run, it's because we gave it the vacant sections to 5. 1, 2, 3, 4, 5. So look at that. On average, it's actually trying to catch it, but on average. So 1, 2, 3, 4, 5. Again, on average, is doing a good job. 1, 2, 3, 4, 5. On average, is doing a good job, right? Again, this one it looks more like an outlier, but again, these ones on average are doing good. On average are doing good, but individually they're not. So that would tell me I need more sections. I need more sections. I need to make my vacant sections smaller. So let's say.
You mean more sections or more dates? Or both?
More sections, more vacant sections. So make the tick variable smaller.
Yeah,
more data points, that's gonna be a bit more tricky because that will depend on how good you want your uncertainty, how small you want it. I mean, Plum, in that paper I showed you last time, we shown that Plum with 20% of the data, with the core, the 20% of the sample core does a good job, but the uncertainties are big, right? So that will be basically it will be up to you to decide how small those uncertainties you're okay with. And those uncertainties, how you lower those uncertainties? By providing more data, by taking more samples, and by taking more core, measure it, and put it into the model. So
cool, thank you.
Yeah, you're welcome. One important thing, one of the things that is in our pipeline is there's a paper by Andres where he basically describes the best method for sampling radiocarbon dates. So in a core of 100 centimeters, for example, he pretty much starts with like 3 samples and then start adding its samples. But there's a method that would tell you where is the best place to reduce the uncertainty on the overall chronology. We are working on a similar method for lead dating, but it's not yet complete. But the point is for users or lab people who are actually able to measure more, to actually know where to take those samples to make the uncertainty of the chronology smaller, and where sort of it's more like an optimization sampling problem. And we have it already for radiocarbon, but the next step is to do it for lead. So it's something that should be coming in the next couple of years, probably. Yeah, so again, so this one ran for way longer. And again, it's doing a good job on the average of 3 centimeters per sample. So again, it's telling us it's not yet there. We need more sections. So that's the best way to check if your run succeeded. Check this little graph that we created here, if the Gauss plots are within the squares. So yeah. Anything else? I think that's everything I need to show you. So any other questions, or I'm happy here to answer them.
I have a question. So what happens when you use more sections than you do have data points? So like, what does it do? You know, like, is it a good thing to interpolate between data points and?
What happens is you have more parameters than data, which is a big over parameterization problem, which could work. Plum actually works on those terms. But if the difference between how much data you have available and how many parameters you ask the method to estimate becomes too big, you will never converge. You will always stay trying to get there, but the numerical method just doesn't get there. So if you see this plot never converging, it's a sign that probably you have too many parameters.
Yeah, okay, sounds good. So like, you know, if you have gaps in your data, I guess that's a bit of a problem, right? When you're sectioning it up.
Not really. I mean, what the rule I use for that thick parameter is how thick my samples were. So, for example.
Oh, okay, so that's what it means.
Yeah, that's why we use 1, because most people use 1 centimeter samples. So so you have your core, and people usually take 1 centimeter and then another centimeter, another. So that's why we use 2. I mean 1 as the default. But for example, if you sample your core every 2 centimeters and you measure and your samples have a thickness of 2 centimeters, then there's not really a point for the method to have a resolution of 1 centimeter. Does that make sense?
Yeah, that makes sense. What I mean is, like, so say you sample, you know, because if you're doing different methods as well, you might be sampling for lead-210, maybe 1 centimeter for the first centimeter, but then you might skip a couple of centimeters and use those for plutonium or something else. You know what I mean? But if you're just looking at lead-210, if you're sectioning, you know, these gaps, like a 1 centimeter at 5 centimeters, and then a 1 centimeter section at 10 centimeters, and then one at 15. What's the best way to go with that? Like, is it section it into however many samples you have, or still use the 1 centimeter?
I would say, I mean, as I show you in that last paper I show you, it's not really a matter of how thick or not the sections are. It's how much of the core you did. So I would say 30% of the core should be sampled to get a good chronology, at least, the very least. The best recommended will be 50%. So 1 sample, yes, 1 sample, no, 1 sample, yes, 1 sample, no. But I will never go below 0.5 in thickness, just because it will create too many parameters. Does that answer your question?
Yeah, that makes sense.
Okay. At least that's my recommendation. That's when I work with cores that people usually send me, I check how thick their samples were. If there's a parse missing, is not really a problem for Plum. Let me show you. Let me show you that a plot from the original paper. This should clarify that. No, it's this one. So this is basically missing data. Strategically missing data basically means 1 sample yes, 1 sample no, so only 50% of the data. And we did the same with not reaching background and with missing the top part. As you can see, the chronology is actually, Plum has no problem of actually creating a good chronology for any of the cases. And all of these were done with the 1 centimeter thickness of bacon sections. So I'll be more concerned into if you have bigger samples than 2 centimeters, their thickness will be bigger than 2 centimeters. that'll be more concerning. Or if you have smaller, for example, your samples have 0.5 and they're continuous, right? If they're not continuous, there's not a problem. Plum would just make a line to that through that sample, and that's not a problem. The problem is when that line has to cross for 3 or 4 samples.
Okay.
Okay.
Thanks very much, Marco. I think it's after 8:30 there at night, isn't it, in Mexico?
Yeah, it's quite late here.
Yeah.
But it was a pleasure to give the course.
Oh, well, thank you very much. And yeah, on behalf of Larissa, Kelsey, and myself, and probably everyone present, we'd like to thank you very, very much for your generosity and giving all this time to us to help explain rPlum, and for being exceptionally patient with all of our many questions, which is something that we're very appreciative of. And yeah, and also for sharing with us your rPlum, which is unpublished code. You know, that's very kind of you to do that. And I'd like to thank everyone for attending, because you've made this a really friendly and interactive and interesting workshop. And yeah, I think I've learned a lot.
Thank you very much. Yeah.
Thanks.
And then next we're gonna go to Kwan and Atum to discuss the data and the models.
Will we?
Marco, Kwan is the person that does radiocarbon here in Australia, and Atum does lead-210.
Oh, perfect. Oh, that's
So
really
yeah,
good.
we're gonna keep using your knowledge, the knowledge that we learned from you with them.
Oh, no, thank you. I'm always happy to hear that people are using the method. So that's what we did it for.
Good. Thank you so much.
Thanks, Marco.
And thank you,
Thanks,
Simon, as
Simon.
well for doing such a good
Yeah.
job in facilitating.
Thanks, Simon.
Thank you very much.
Thanks, everyone.
Thanks,
Thanks,
Marco.
Marco.
Oh, thank you,
Bye.
everyone.
Bye, everyone.
We'll be
Bye.
in touch, Marco, about future workshop, a follow-up one.
Sure, sounds good.
Yeah, but next week you've got a break from us.
Sounds
Bye.
good.
Okay.
Bye.
Thank you.